I'm going to start the recording. I'm going to switch my video. And we are going to pick back up. We were talking about exponential functions last time. So, if you'll remember, an exponential function is one where the exponent is actually a variable. So at least somewhere in the thing, we've got something with a variable in the exponent. So it ends up looking like this, where we had y equals 2 to the x. Okay, so we graphed those last time, and we found out that if we were dealing with a number that's bigger than 1, that our graphs end up looking like this. They have a horizontal asymptote at y equals 0, and they're always starting down really close to the asymptote and then shooting up toward infinity. I didn't put an arrow on that guy. So they always go up and to the right. If they are the base here, remember the base, this is my base, this is my exponent. So if this base is bigger than 1, right, then they always look like this. Okay, we had a few rules that we said, hey, this is what's happening with all of our graphs. We're always going to have the point 1 in the base. We're always going to have the point 0 and 1. And we're always going to have the point -1 and 1 over the base. Okay. And then as long as we haven't shifted, these things all happen before we shift. So then we always have that horizontal asymptote at y equals 0. And then we graphed one where we said, well, what if it's not bigger than 1? What if it's between 0 and 1? So then I've got like fractions, and those guys start at the top and come down. They still have all that stuff we mentioned, like they still have the point 0, 1 right there, but they're going to come down and go to that asymptote. So they're decreasing that way. And I think that we ended up, I got cut off by the bell, of course. We were talking about compound interest, so that's where I'm going to pick up. We had the formula for compounding whenever it's like annually, semi-annually, monthly. Remember, monthly compounds would be 12, quarterly compounds would be 4, stuff like that. If it was daily compound, it would be 365. So we did one of those, and that's where we were when I ran out of time. And I'm going to say that this is the 4.1 homework in your Math Excel. So you should be able to do that homework, except for we just have a couple of little pieces that we're going to pick up. So I'm going to talk a little bit more about compounded interest, and then we'll pick up some transformation stuff. So the other thing, so we have that one compounding interest, but the other formula that sometimes we have is for compounding continuously. So I was actually at the Dallas Zoo one time, and you have to walk through a tunnel to get into the zoo. And in the zoo, it said, in that tunnel, there was a thing up on the wall, and it was a digital bulletin board, and it was changing all the time. And it said, the current population of the world is, and it had this big, huge, long number. I don't remember what it was. But if you stood there for just a second, it was changing constantly. So you could always see, and it was pretty much a growth pattern, right? Our population is going up, not down in general. So you could see that. And as I was looking at it, I realized that they are probably using a continuous compounding situation. So what that means when we're dealing with compounding is, so if we started with 100 people, and then we had 10 births, okay, well, tomorrow we have 110 people, but then in a few years, those people might be having babies, right? So then we've got births on the kids and stuff like that. So it just, it compounds, it adds up very quickly, because it's not just interest on the first people, it's a rate on all the other people that are added, basically. Okay, so a lot of our compounding, whenever we're talking about growth models in particular, they're going to use a formula that looks like this. A equals PE to the RT. Okay, I tend to call this the PERT formula, even though it's not really, because the R and the T are up in the exponent. Okay. Because I'm going to have variables up here in the exponent, that tells me that this guy is an exponential function, right? The variables are going to be up here on the top. So this one, again, you're not going to have to memorize it. You're just going to have to recognize it. okay? And we'll know it's the continuous guy because it's got this E in there. So E is an unusual guy, okay? You may not have ever seen him before. E is like pi, okay? It's an irrational number that we assign a value to. So when we see pi, for instance, we know that's a variable, that's a Greek letter, right? So we know it's a variable, but it's not really variable because we assigned it a value. So we know that we're going to call pi, like if we were given it a value in a problem, we probably could say 3.14. Right? Everybody pretty much knows that value. We know it's longer than that, irrational, and it's also continuous, non-terminating. So we know this goes on forever, but we just approximate it, right? So for E has an approximate value, and we just give it to it. Of 2.72, okay? And again, it's actually like 2.718, blah, 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 blah. Like if you went on your calculator and you punched the E button and told it to give you an equal to, it would give you a long decimal, okay? This number, it's called the natural number. Okay. So when we get to logarithms later, we're going to have something that's called natural logs, and it's going to be based off of this E guy. So I want to just show you that on my calculator real quickly. Your E to the X button, you have this ln button here if you're using an 83 or a CAS or something like that. E to the X is up there, okay? So I'm going to use that. I have to use my second button to get to it, so I'm going to use the second and the ln, and see how it says E to the raised to the power. I can put second, third, fourth, whatever. I'm just going to put fourth or first because I want it to give me the value for E. So when I punch that, look, 2.7182818 da 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 da. So that's why we abbreviated or approximated it for 2.72 because we don't want to deal with this really long decimal. So whenever we see it in our heads, we can kind of think, oh, that's a number between 2 and 3, basically. We could put it on a number line, all that kind of stuff. It has a value. But what we're going to see is there's going to be stuff where we use this compound interest formula. We're not actually going to put in a value. We're going to use our calculator, and the calculator has it stored in there, which is the nice thing. Okay. So the example for this is actually going to be the second part of the example we did earlier. So in the example earlier, it said, we invest $8,000 at 7% compounded monthly, okay? So instead of the 7% compounded monthly, we're going to put the same amount of money in. We invest $8,000 at, and the different interest rate is 6.85%, and it'll say compounded continuously. Okay. And whenever I see that compounded continuously, this is what tells me, oh, that's going to use the natural number. That's where I'm going to use this formula PERT, because this one is specifically for when it's compounded continuously. So what did they mean by compounded continuously? Well, when we were compounding monthly, well, that's just once a month. But continuously is like, okay, now it compounds. Now it compounds. Compounds now, it compounds now, it compounds now. It is always compounding. And that's kind of what happens when we're doing growth functions, is they're always compounding. So it's that continuous thing. So we invest $8,000 at 6.85% compounded continuously. The problem earlier said we were going to leave it for 6 years. So we're still going to keep that for 6 years. Okay, and the actual problem, I split it in half, but it said first do it compounded monthly, which we did already, and then it said second do it compounded continuously, and the question said which one is better. Okay, that's what they actually asked me. So we're going to compare them in a second. So here we go. Compounded continuously. The nice thing is the formula is going to be there. So A equals PE to the RT. Okay. Again, P is the same P as it was last time. So, and A is the same A. So this is the amount at the end. Okay. E is the principal, which means it's the amount at the beginning. Okay. The E, it's going to be the natural number. So we're just going to plug that point, use that button on our calculator. Okay. And then the R and the T are actually the same as they were last time. So the R is the interest rate. Okay. And remember, we're not going to punch 6.85% in our calculator. We're actually going to change that to a decimal. Okay. So it's the rate as a decimal. And the T was time in years. So everything is just like it was last time, except for this little E guy that we're sticking in. Okay. And of course, the function looks a little bit different, but we're going to use that guy, that particular function. So let's plug in. What is my principal amount? The amount we're going to put in, P equals 8,000, right? That's we're investing amount, $8,000. Like I said, E is just going to be a natural number. We don't need a number for it. The rate is going to be R equals, instead of 6.85, I'm going to go ahead and make that a decimal. So 0.0685. And you don't have to write the 0 first, but you do need this decimal in here, right? 0.0685. And the T, time in years, that is just going to be a 6. Okay. So these are not so bad for figuring out what's what and substituting in, but we got to make sure we're using our calculators correctly when we do this. So I'll spend a little time with that. So my formula is A equals, we don't know that guy, but we're going to put in the P. We said that was 8,000. Okay. Times E, and E is being raised to the RT, right? So E is just going to stay E, because it's got its own value. But the R we said we're going to use is the point, and I'm going to put parentheses, 0.0685 times the T, which is the 6. Okay. So again, if you want to try to punch all of this in the calculator all in one big line, you feel free, but I generally like to work these out in steps. So I'm going to scoot so we can see the calculator. So to work these out in steps, I'm going to do, okay, look here. Excuse me. 0.0685 times 6. That is going to be 0.411. So this is going to turn into A equals 8,000 times E to the 0.411. Okay. It's, to me, easier for me to punch that on my calculator, E to the 4.411, than it is to try to make sure that the calculator does the multiplication first before it finds the value. Okay, so I need to do E to the 4.411. I'm going to use that LN, that button right above it again, the E raised to the, so I need second and the E raised to, and, you know, spend some time as you're starting to do your homework and make sure that you can do this, because you're going to have to do it on a test. So E raised to the 0.411. Okay. And that's going to give me a decimal, 1.5 something something. As much as possible, keep those decimals in your calculators, because we don't want to have rounding errors. We're going to try to keep them like they are until the end, right? So E to the 0.411. And then we're going to multiply that. That was this value. You want to substitute it in, you can, but this is this value times the 8,000. Okay, so my answer is $12,066 and 60 cents. That's not going to round, right? Okay, so there we go. If it was compounded continuously, that's how much money I would have at the end of 6 years in that account, right? Okay. So last time we did this and we had, I'm going to stick it right here. Did I do this? Yeah, okay. So I felt like that was a wrong answer, but it looks right. So last time we did this and we had the $12,160.84. It was only compounded monthly. The one we just did is compounded continuously. But the difference is, if you look at it, they had a higher interest rate, right? 7%. So we had $12,160 here. Here, this one, we only have $12,066. So the question is, if I'm investing this money and I want the most money out at the end of 6 years, which one's the better investment? Okay, and the answer is, in this case, it's the compounded monthly. And the reason is because the interest rate's better, right? It was 7%. And this one that we just did was only 6.85. Okay, so it's not always just compounded continuously is better. You also have other factors like what was the interest rate. So that can sometimes make a mistake or make a difference. Okay. Does everybody see how PERT works? PE to the RT? Okay. So with that in mind, the question comes up, well, what the heck does it look like when I graph y equals e to the x? Okay. Because we've introduced this lovely new constant for us. It has a value 2.72, right? What's that graph going to look like? So we're going to have to kind of fall back on some of the rules we had the other day. And what we said was, if we're not shifting it, which this is the parent function, right? I don't have any pluses or minuses or multiplied or whatever. If we're not shifting it, then we know we're always going to have a few certain points. Okay. X equals 1, X equals 0, X equals -1. Okay. And let's see if we can remember what's going on. Whenever it was X equals 1, we got out e to the 1, which is just e, right? Okay. So I have the point 1 comma e. And to graph that, I'm going to have to say, okay, this is a point somewhere between 2 and 3, right? So the y value here, the e here is about 2.72. Okay. I'm not going to get an exact value for that, and that's okay. I'm just going to say it's up here between 2 and 3, kind of close to 3, right? These are just sketches. They don't have to be perfect. And then we had a point, we said anything to the 0 power was a 1, right? Okay, so we always, if this guy is bigger than 1, which it is, have this point 0, 1. So that point's going to be on all my graphs. Okay. And then when it was a negative, remember we said anything to the -1 is going to flip it, right? So instead of e, we're going to have 1 over e. Okay. And I don't know what that value 1 over e is, but I know that anything 1 over a, stick an e there. Nope, I pushed the wrong button. Dang it. Here we go. Anything that's over a 1, bigger than a 1, that's going to turn it into a fraction, right? So I'm going to punch 1 over e just to kind of get an approximate value. So this is about 0.3637, I'll say. Okay. So again, that is going to be -1, and it's a value down here, getting close to that 0, right? And the fourth thing we know that we have on all of these guys is we have that horizontal asymptote, y equals 0. Okay. So E has a value that's bigger than 1. And sure enough, when we go to see this graph, it looks very much like the graph we did the other day of e to the second, or I'm sorry, 2 to the x, 3 to the x. We talked about the 5 to the x. They all look the same, right? It's just a matter of where those points come out exactly. Okay. So he's going to graph just like all the others, and he's going to have shifting like all the others. So that's the next thing we need to do. So we'll just use this one and we'll say, okay, what do you think is going to happen if I have, I'm going to put it right here, y equals e to the x minus 3. And I know it's been a while since we did transformations. So we have to kind of go back in our data banks and say, okay, what was this? Shifting happens whenever I'm adding or subtracting. Whenever it's on, remember, this is my function, e to the x. This is being subtracted on the outside. If you'll remember, that was a vertical shift. I know it's been a while. This is a vertical shift. So this is either going up or down. We don't know which one yet because I'm adding or subtracting on the outside of the function. So my question becomes, which one is it? Is it up or is it down? It's down, right? Exactly. So it's going to shift it down, and we know it's going to shift it down 3 units, right? So I think with these exponential functions, I think it's easier if I shift the horizontal asymptote first, and then I have the rest of the graph kind of follow it, okay? So this was at y equals 0. If I move that down 1, 2, 3 units, -1, -2, -3 on the y, then that's going to make my new horizontal asymptote right here. It's going to be y equals -3, right? So I think if you'll move that one down, it makes it kind of easier to see what happens with the rest of the points. So this was the point 0, 1. If I move it down 1, 2, 3, I'm going to have it, let me do this a different color. I'm going to have it right here. It's going to be 0, -2, right? Okay. So, and it should look just like the one above, it's just been shifted. So this one above was exactly 1 unit above, and this one is exactly 1 unit above. Okay, and then I can do the same thing with this point. It was 2.72, so now it's down 1 is 1.72, down 2 is 0.72, down 3 is going to be not quite whatever 1 minus 0.72 is, I don't know. Like it's about 20.28, right? Something like that. Okay, so right there. And then this third point was just barely above my asymptote. So when I shift it down, it's going to be 1, 2, 3, right here, barely above the asymptote. So the reason I think move the asymptote first, if you see it, is because everything should still be in the same physical approximation close to the other things. So whenever I graph this, kind of dot to dot it, okay, it should look very similar. It's just moved down, okay. So that's kind of what a vertical shift looks like. And then of course we know we had horizontal shifts and stuff like that. There's always the multiplication, which stretches stuff, but for that, I'm probably going to use a calculator. But these shifting, I think we can do shifting fairly fast, not too bad. So I'm going to do this one in green. Next one, move this up a little bit. We're going to do y equals e to the x plus 3. Okay. This one is adding or subtracting inside of the function. So if you remember adding and subtracting inside of the function, that's going to give me a horizontal shift, right? Okay. So I didn't finish my thought up here. This is vertical shift down 3. This one's going to be a horizontal shift, which means either left or right. And if you'll remember, it's inside of the function. We can see it's inside the parentheses with the x up there in the exponent. They don't always have to be inside of parentheses, but if they're still in the exponent, we know that's inside of this exponential function. So it's horizontal, and when it's on the inside, it's the opposite of the sign, right? So it's not going to go right 3 because it's positive 3. It's going to go left 3. So remember this equated to shifting around the x or the x-intercepts. Okay. In this case, I don't have x-intercepts because we're never actually touching that y axis, but I do have points there that I can shift to the left, right? So I'm going to start over because this graph's getting a little bit full. I'm just going to give real quickly. The original was right here, y equals 0. And I had a point here. at 0, 1, and I had a point here at 1, almost 3. So there we go. That was the sketch of the original. Okay. I'm just redrawing it so that we know where we started. There's my e to the x. All right. It won't look, hopefully it won't look quite so lettered on my graph. Okay, here we go. So this says shift it to the left 3. So I'm going to do the same thing I did before. I'm going to talk first about the horizontal asymptote. And I look at that guy and I say, oh, that horizontal asymptote, shift him left 3. Does that matter? Well, it's just the line y equals 0, right? And it's all the way to the left and it's all the way to the right. So if I shift it to the left, that line is not changing, right? It's staying where it is. When I shifted it down, yeah, it moved because it's not at y equals 0 anymore. But left or right, I'm going to still have the same asymptote, y equals 0. That's not going to change. It's the points on the sketch here that are going to change, right? So for instance, this was the point 0, 1. But I'm saying I'm going to move it to the left 3, -1, -2, -3. So instead of being 0, 1, it's going to be -3, 1. So think left and right. I'm not moving that point up or down, right? It's still, the y value is still 1. Okay, it's just the left to right, which means this is affecting my x values, right? Because it's inside of the function. So that guy moves over 3. Okay, and then there was this little point here. I didn't put him on my original, but we know that at -4, there's going to be this little bitty decimal guy. If that helps you to graph, then move him too. It's fine. But then to move this point 1 and E, right? That's this point 1, E. To move him to the left 3, again, the y value is going to stay the same. This does not affect what's going on in the y. This affects left and right, which is my x values. So instead of 1, when I subtract 3, I go to 0, -1, -2, right? So I end up with this point, and I'm going to stick it over here, -2e. That's what happened. This guy is shifted left 3. All right. And now I've got enough for sure that I can give the basic shape of the graph. And there it is. Remembering that your asymptotes act kind of like magnets. So they're going to pull it down and it's going to be really close to what I've got over there, whatever my asymptote is. Okay. All right. So that's the idea behind the shifting of these guys, and it works the same for any of them. So if I had that graph where I had the base was a 1/2, find him real fast. Okay. He looks like this. Remember, he's coming down, so he's going this direction, decreasing, but same thing. If I move him down, I start with that asymptote, I move him down. If I move him up, I start with the asymptote, I move it up. Okay, left to right, same thing. So they all function the same way, which is kind of nice. All right. Is everybody okay? No worries. All right. Well, that's the wrap on the 4.1. I don't have a ton of time. I am just going to tell you the lead into logarithms. And then on Friday, you'll have a big video on logarithms. So that's where we're headed. So I want to give you just a little bit of background information. And the important thing, logarithms is a weird word. Logarithms are exponents. That's what I want you to remember. Okay. Logarithms are exponents. So whenever we've dealt with earlier, we dealt with things like, x squared times x to the third. And we said we were going to multiply the same bases. Then we ended up adding the exponents. I'm not going to do this right now, but what we're going to see is that logarithm properties, we're going to see those on Friday on your video, they're going to work the same way. So if I'm multiplying the like bases, then I end up adding the exponents. So since logarithms are exponents, and I'll show you how in just a second, all the rules for my exponents are going to apply. They work here. Okay, so it might look a little bit different whenever we put them together, but they're going to work. All those rules are going to work very, very similarly. It just looks a little bit different because the notation is weird. Okay, so I'm going to give you a notation real fast. We're going to see how to switch back and forth between exponential functions and logarithmic functions. And then I'm sure I'll be out of town by then. Okay, so logarithms are going to look like this. We know that an exponential function looks like y equals b to the x, right? And we said whenever we see it in that format, it's y. So this is my answer. Answer equals some base raised to the exponent, right? Those are the words we're using. Okay. So that's what's going on with exponential functions. And what we're going to see is logarithms are inverses. Logarithms are inverses of exponential functions. Okay. So here's how it works. If I have this x up here in the exponent, sometimes I'm going to want to get that exponent down. Okay. Sometimes it'll say like solve for x or something like that. And you're like, well, wait a minute, that guy's in the exponent. I can't do anything with him. Logarithms are the mechanism we use to get the exponent down. Okay. So that I can then work with it and solve for the exponent. So this is just a way of rewriting an exponential equation or function to be able to work with that exponent. Okay, that's what we're doing. And so the notation is a little cumbersome at first, but once you use it several times, you will see it. So this is what a log function looks like. And I'm going to say it like this. Log base exponent equals answer. That's like a Webster saying. Okay, so if you like that, you can steal it. Log base exponent equals answer. Log base exponent equals answer. Log base, I'm sorry, I just lied to you. I was like, that doesn't sound right. Erase that. I'm so sorry. Log, I'm like, why doesn't that sound right? Log base answer equals exponent. That is much better. I'm so sorry. My mind is straying. Log base answer equals exponent. Okay, so the idea here is that we're going to get the exponent all by itself. Okay, so it's going to be on the other side of the equal sign. Log base answer equals exponent. That sounds much better in Webster brain. All right, so back up here, remember that we had the base and we had the exponent and we had the answer. So this is going to translate, it's going to look like for this one up here, the log, and it's actually literally the word log, stands for logarithm. The base, well, that's just the b, whatever that is, and we'll have some experience going back and forth, so we'll see this. Log, the base. The answer was the guy that's over here on the other side by himself, right? So it was the answer equals the base to the exponent. So that's the y. And that's all going to equal whatever the exponent is. That's what it looks like. So if you want to try to memorize that one, you're welcome to memorize that one as well. But sometimes I think the wording log base answer equals exponent, having those words in my brain helps me. Okay, so if it helps you, then great. If not, then feel free to just memorize that guy right there. But notice what it does. It gets that x down out of the exponent. It gets by itself. Okay, so I think we have time to do one example each direction maybe so we can see what the heck is she talking about. Okay, so let's talk about this guy. My example is 3 equals log base 7 of x. So what it says is write it as an exponential function. Write it as an exponential function. Okay, so in my head, I'm thinking it's the log with the base. So this 7 is going to be my base. So that, remember, is going to be the bottom whenever I'm writing an exponential. Log base, this is going to be my answer. Okay, so that's going to go on the other side of the equal sign. And this 3 is going to be the exponent. So that's going to come up here. So base to the exponent equals answer. Log base answer equals exponent. Okay, this is it. That's what it would look like as an exponential. And then we can actually plug that value in and go, what's 7 to the third, and get some number. I don't know what it is. Okay, I don't really care what it is. What I care is that we can rearrange this so that, okay, I couldn't solve this log guy, but I can solve this exponential, and it works the other way around too. So the other way, an example looks like this. Rearrange 12. I'm sorry, let's do this one. B to the third equals 8. Okay, and it'll say something like, write it as a logarithm function. Well, let's do it. Log, the base is the B, so that's going to go down here. The answer is the 8 equals the 3. There you go. Okay. Is that your bell? Ah, man. Okay. So you can do the 4.1, and there's a video on logarithms for Friday. Have a great week. Thanks.